there. As Teresa mentioned, my role here at University Lab Partners is involved in helping support the accelerator teams, as well as helping support our incubator companies here at University Lab Partners in advancing with fundraising and commercialization and growth. So I'm very excited today to have our speaker, Atul Mahajan, the Director of Engineering at IZEAL Healthcare. So I've known Atul for a fairly long time, back from his bioengineering days at Arizona State University. So we're thrilled to have him presenting today. And he's a seasoned global leader with over 20 years of experience in engineering, project management, project development across Fortune 500 companies in software services, semiconductors, and medical devices. He excels in managing cross-functional teams, ensuring compliance with GXP, FDA, ISO, and IEC standards, and driving business transformation through data-driven methods. As a Six Sigma Green Belt, Atul specializes in process improvement, cost savings, and revenue growth while overseeing product development from concept to launch. Thank you so much for being here today, Atul. And I'm going to turn the presentation over to you. And as Teresa mentioned, feel free to write your questions in the chat. And I've also put a short survey in there that will allow Atul to have a better sense of your familiarity with the topic of DFM. So if you want to just take a few moments to fill out that survey, that would be great. Thank you.
Hi, everyone. Good morning. Can you see my slides?
Yes.
Okay, awesome. All right, so thank you, Charla, for introducing me. As Charla mentioned, I have a long history in medical device industry, over 20 years. A lot of that has been with Stryker and now with IZEAL. Before that, I had short stints with software and semiconductors. I've been in Arizona for almost 24 years. Did my master's in electrical engineering and MBA from ASU. So as Charla mentioned, been in industry for a long time, have done a lot of functions from advanced manufacturing to operations and digital transformation, also in some global roles at Stryker. So this topic is pretty close to my heart. But before we jump into the topics, just want to share a little bit about IZEAL Healthcare, what IZEAL Healthcare is. Well, IZEAL Healthcare is a global engineering, software, and regulatory service provider. We are based out of Minnesota, but have tech centers in India as well. So what we do is we work with our clients using competence, integrity, trust, and being equal partner to provide CE compliant solution, US FDA, apply a lot of design for Six Sigma approach. We have a strong background in statistics, and we have a team of engineers that can support design, process development, validation, quality, or regulatory stuff as well. So from an expertise point of view, we kind of span across the spectrum. We can support design-related initiatives, programs, projects, process-related, some software development. Now with AI, we're focusing on some digital health as well. So a lot of opportunity there. We can set up quality system, manage CAPAs for post-market surveillance, and for mature companies, we also do some acquisition integration and some remediation kind of work. So where does the DFM kind of come into picture? So I would say where the design is ready to be transferred, or when you are thinking about process development for your design, that's where the DFM would come into picture. So we do a lot of DFM related work with our clients, also internally when we design products as well. So what IZEAL does is we can provide end-to-end solutions, or we can also provide outcome-based delivery as well on any of this area across the spectrum. So this typically start with gap assessment and work with our customers to find out where the gaps are, where the help is needed. So obviously we do that through highly skilled resources with a hybrid cost model. We can do onshore, nearshore, offshore arrangement as well. And we have a strong project management that provides a lot of value in terms of getting the deliverables completed with your teams. So that's a little bit about ISO. Obviously, DFM can come into picture across this product realization cycle when we're creating strategy or when we are doing a gap assessment, and mostly when we are doing process development. So the DFM kind of plays an important part in the product life cycle as well. Okay. So let's start with the design for manufacturability. Before we jump into definition of design for manufacturability, I'd like to see your experience with DFM. So I have posted this created this poll and Charla has shared that one. So if you had a chance to give the responses, that would, if not, take a few seconds and
Yeah,
submit your
here, I'll put it back in the
responses.
chat for those people who just jumped in. If there's a short poll here, if you want to just fill that out so that we can have a little bit better sense of where you're at on the DFM scale as far as understanding. Okay.
Responses are still coming, so I'll wait for a few more minutes. At 15 right now out of 38 participants. Okay, all right. So let's see what the participants are saying. So around 55% of folks on the call are new to the topic. Around 30% can describe. Some have done with the help of others. Oh, the response is coming. But the percentages are pretty much similar. So 50, close to 50% new to the topic, 30% can describe, and then obviously others are very new to the topic. Okay. All right. So that's thank you for submitting the responses. All right. So the topics that we'll cover, as Teresa mentioned, so we'll basically go through an overview of DFM principles and their importance in product development. We will see how early stage companies can benefit to reduce cost and time to market. We will review some key factors that are essential for DFM and also common pitfalls to avoid. We will look into how we can balance innovation and practicality for small scale launches. And then finally, how we can collaborate with manufacturers to optimize your design. So these are the topics we're going to cover throughout the presentation. Oh, one more, identifying the risk as well, because the risk is a big factor in manufacturability because they can become costly problems. So what is DFM? So the definition of DFM is basically it's a general engineering art of designing the products so they're easy to manufacture. So keywords are highlighted easy. It's a proactive approach that integrates your manufacturing considerations in the early design stages. Again, proactive and early is highlighted here. If you look at the bookish definition, somebody named Boothred and Dewhurst wrote a paper in 2002. So they're calling it concurrent engineering studies to provide guidance to the design team in simplifying product structure to reduce manufacturing and assembly cost and quantify the improvement. So it's all about how easy I can make it, how early I can start the process of thinking about the manufacturing aspect, how proactive I can be, and then can I provide a guidance to the design team so that they can simplify the product to reduce the cost and identify the improvements. So what are the expected outcomes? When you think about applying DFM, there should be some benefits of it, right? So some of the benefits could be you will have fewer parts, fewer assembly operations, some foci yoke or error-proofed assembly, robust design transfer. So these are some of the outcomes you can expect, and that will lead obviously to lower cost, direct and indirect cost, better product quality, and also less design changes down the line when you're scaling the production. So the question is DFM a must-have or nice to have? Can I get away without it? So let's explore that as well. Now, there are other design for, you might have heard, design for sustainability, design for reliability, design for XYZ. So I put some here with the acronym CARS. So design for cost, reliability, assembly automation, and sustainability. So this whole idea about design for X is a new ideology that has been kind of socialize. It's called design for excellence. So you can have design for cost, reliability, etc., in addition to design for manufacturing. Now they're all interconnected, as you can imagine, because it's all kind of leading to the same goal. And sometimes the DFM can also be confused with DFA. So, but there are two separate methodologies. So they can be combined in a single topic, design for manufacturing assembly, but sometimes their purposes are different. So just wanted to share what our other design for are out there besides DFM. Okay, so why is this DFM essential in product development? So let's talk a little about why. So first and foremost is the user experience. So if you consider manufacturability, obviously you can have high quality and reliability in a product at lower cost, faster availability, sustainable products, and use and maintenance. The product is simple. You can go to market easily, have it last longer, and then have some high reliability as well. Second aspect is company bottom line. So the manufacturing company or the company who's wanting to launch the product wants to earn profits. So if you have less production cost, shorter development time, uh, high quality of in line quality, then less complaints in return, obviously that adds to the company bottom line. The third aspect is environmental. So if you have less components with robust design, it will lead to reduced material waste, low energy consumption because you'll need less raw material, and also it will reduce the pollution. Safety and efficacy as well. So when you consider manufacturability, you can mitigate a lot of harms that could come into the product because of different features. Accuracy of diagnosis, if it's medical device, it can help in the end goal of the product being able to diagnose conditions easily. Effective treatment, less failures, and zero recall. So these are some of the factors that are really essential when you consider DFM in the product development. So where does the DFM fit into the product development cycle? Many of you may be on the journey to design your products. You may have concept, you may be designing a system already, you might already ahead of the curve and might be in clinical trials. So this is like a V-shaped diagram that typically is used in design and development, starting from concept all the way to release the product. So as we look at this, where does it fit into, right? So when we have functional specification, and when you want to translate those into requirements and especially the performance requirement, that's where you would consider some of the DFM related inputs. Then when you also want to translate the requirements into physical form, that's another area where the DFM can come into picture. And then obviously at the end, when the product value is based on consistent delivery, when you kind of realize, that's when you say, okay, did you meet the DFM goals or not? So these are some of the areas where the design for manufacturability comes into picture, because the goal is to fulfill the requirements efficiently. Yeah, so where is the sweet spot then? So having a narrow to a primary concept prior to committed implementation would be a sweet spot for DFM timing. So you have the requirements, you have the concept, now you're getting ready to prototype it or build some samples. That's where you need to consider it. So why should early stage companies bother about DFM? So obviously it's a strategic advantage, because if you start thinking about the end product and how effectively and easily it can be manufactured, lower cost, that gives a strategic advantage. It can accelerate the time to market, have scalability, also improve the product, lower long-term cost, and also can contribute to your culture, because everybody's thinking with the manufacturability in mind as you are designing different products or working on different prototypes, iterations, and so forth. So it gives you a strategic advantage. Compliance and certifications. Obviously, if you have a simpler product or consider the product with less issues, then it will reduce the compliance roadblocks. You can meet the new standards and also enter into new markets. The third thing is about resource efficiency. So with your limited budgets or funding, you can optimize the resources and avoid a lot of waste, increase the collaboration, and also preserve your cash. And finally, increase chance of success. So as you have robust design and it's manufactured with some of the principles I'm going to talk about later in the presentation, it will lead to less failures, have better customer satisfaction, and also increased interest from investors and partners. So all these are kind of key benefits that you can achieve through DFM. That's why the early stage companies should pay attention to the design for manufacturability. So what are the key principles? Now, key principles, you can write a whole book about it. You can define them, categorize them differently. But I thought of a few categories here. So first thing, manufacturing process itself. So how I'm going to manufacture my product or part. So choosing a correct manufacturing process for the part or the product is essential. Then considering the quantity, material use, complexity of the surfaces, tolerances, processes, post processes or inspection, those kind of things come into picture as well. So first key principle is around manufacturing process. The second one is about product design itself. So using standard off-the-shelf parts wherever possible can reduce a lot of custom manufacturing cost. It can create interchangeable components to streamline assembly and repairs. So the second category is product design. The third category is operating environment. So what are the principles related to operating environment? So assessing the environment in which the product is going to be used, humidity, temperature, extreme conditions, maybe special need requirements, and so forth. The fourth one is the material itself. The material can be a huge category where you may spend a lot of time in choosing the right material, readily available, scarcity down the line, maybe obsolescence, those kind of things. But more importantly, ensuring that material meets your functional and environmental requirement. So material can be a big category for consideration. Compliance and testing is another one where design features that can simplify inspection or quality check, performance testing. That's another category of principles. So these are the 5 categories we will focus on today. There may be some others, and you can certainly research those as well. So how do you balance innovation and practicality? So in case of startups, a lot of times we think about, okay, how do I go about, creating an innovative product and at the same time make sure that it's feasible, right? So having focus on starting small but thinking big, early collaboration. So you can have some early collaboration going on. Again, interchangeability of components, easy transition to mass production, rapid prototyping, and avoiding over customizing. So these are some of the areas where you can consider when you're balancing innovation and practicality. Now, additional considerations could be supply chain resilience, as I mentioned, about obsolescence or product scarcity, or material scarcity, cost management strategy. You should have cost management strategy in terms of, okay, when I'm starting out and I'm just going to launch 100 units, how much is the cost going to be, and how much my cost is going to be for next 1,000 units, and so forth. Obviously, regulatory and compliance readiness, risk management is also another tool you can use to balance some of the innovation and practicality. Contingency planning, strong project management, continuous improvement. So these are all things you can consider when you're thinking about how do I balance the innovation and then feasibility of the products. Now, collaborating with manufacturers is one of the objective or the topics we want to cover today is like, how do you collaborate with manufacturers? What are some of the things that you can think about when you go to a machine shop or go to a contract manufacturer and say, okay, hey, I got a design. I need you to help me manufacture, right? So the first step is basically engaging with them. Who do you engage with? How do you engage? So what can you do? So obviously the first step is understanding manufacturing capability. What can they manufacture? What kind of processes do they have? Is that the process you're gonna leverage for your manufacturing? Assessing the tooling and equipment. So if you have some tooling and equipment related considerations, and so 3D printing versus PET versus CNC machining or other manufacturing methods, do they have that equipment now? And obviously the material constraints. So these are some of the areas you can start with in order to engage with the manufacturers. The second thing is analyzing. So share early with them your design, get some inputs on manufacturability, share with material selection, some of the process limitation you can start understanding. Obviously update your design, update them on your design progress, gather feedback, use some communication channels with the project manager or point of contact that you may have been talking to, and then maybe do some joint design review sessions. So after engaging with them, start analyzing your design, their process limitations, and so forth, and keep them posted. The third step would be treating. So obviously, once they give you feedback, don't just keep the feedback aside. Make sure you incorporate the feedback, iterate with alternative materials and processes if needed, and work together to test different prototypes before freezing the design. And finally, you have to adapt. You basically create more of a collaborative long-term relationship with them and then align with their technology roadmap as well, because sometimes they may say, okay, well, we are moving away from this process to the next gen process. How does that align with your timelines? How does it align with your manufacturing aspects and also the cost considerations? So these are the steps you can take to engage with manufacturers in your process. So we also have another topic, we talked about manufacturability risks before they become costly problem. So what are some of the steps you can take to address your manufacturability risks? So obviously follow DFM guidelines, create a DFM checklist to address critical areas. Second step is you visit and audit manufacturers to understand their capabilities. We just talked about that, identify what are the risks. Another step is to conduct your own risk assessment and failure mode analysis. So make sure that you are identifying those early in the design. And then also select reliable materials. Work with suppliers to meet your quality standard and lead time. So making sure that the materials can be sourced in time, and then you have robust suppliers to that. And then obviously validate your design features that are aligned with intended manufacturing processes. So early stage startups can reduce some of this risk by identifying the risk proactively, integrating best practices, and then collaborate with the manufacturers early on. So that's good. So we talked about what is DFM, why we should do DFM, why we should consider DFM, why should early stage startups bother about DFM, how do we reduce the risk, how do you balance innovation and practicality. So now let's dive into how to achieve DFM, right? What are the strategies, those key principles we talked about, what are some of the details there? So we talked about one of the key principles was related to manufacturing processes. So how do you go about selecting a manufacturing process? What are some of the considerations or tools and techniques you can apply? So the goal here is to select the process that is optimum. So the optimum selection is the goal. So minimizing number of steps, how do we do that? So we minimize the number of steps with manufacturing methods limitations in mind, and achieve the assembly goals or the automated production. So if you want manual assembly, you want automated, so you basically optimize your process. So select the optimum process that is suitable for your product. Now, how do you go about that? So you can create a process map and workflow, assess your product process fit, just like a product market fit. Does my product fit into that process? Combine some of the assembly steps wherever possible. As mentioned, make sure you have required fixtures to avoid human errors. Review the need for specialized tools. So sometimes specialized tools may not be available. So if you need to invent them or create them, that can add to your process related timing and considerations. Assess inline inspection. Think about what can you do to inspect some of the features, some of the functionality, and then you can conduct some design of experiments, statistical modeling, process simulation. Those are more advanced tools. But if the process is simple enough, I think just thinking about how would an operator assemble the product? How would an operator manufacture this? What are the machines that are needed? What are some of the inspections that are needed? So that way you can optimize your manufacturing process. Some other considerations to take into account while you're doing that, obviously labor cost, labor skill set and availability, that kind of applicable for when you're going high volume or from contract manufacturer. Obviously the material, the volumes you're gonna, with this high volume or low volume. If you have multiple variants, it's there's high mix, low volume, those kind of scenarios. Obviously tolerances. Another thing would be scrap rate. What's the cost of scrap? If I have low yields, am I gonna have a lot of cost related to the material that is going to be scrapped? Then layout, all those things. If you're thinking of in-house manufacturing, then the layout, automation, all those things can come into picture as well. Okay. Second area we looked at was product design. So what is the goal for product design? So product design goal is to reduce number of parts to simplify the design. So if I have a design where I have a lot of sub-assemblies, can I simplify those? Can I combine some of those assemblies? So a couple of techniques there are essential component analysis and detailed functional analysis. So we can look at these two techniques in a bit of a detail, just to give you a flavor. So what is the essential component analysis? Essential component analysis is a decision tree-based approach where it challenges each component's existence in design. So for example, if you look at the left part, you can question, why do I need a joint here versus a single piece instead of having two pieces? So you need to kind of follow design tree to challenge and justify each component. Detailed functional analysis, on the other hand, it's more of a documentation of functional relationships between the component among the components in the system. So if you have, let's say this is a flange in other part, you can define the relationship between those two and see what can you do to reduce the number of parts if they are providing the same function or they're complementary and etc. So what does it allow to achieve, right? So speed, obviously. So even for large number of components, you can expedite some of the things. You can evaluate, you can basically evaluators can acquire common rationality, justify. You have to kind of make sure you're aligned with the design aspects. On the detailed functional analysis side, obviously you can benefit from participants with multiple roles to understand why and how the design is structured. You can eliminate when the functions are reassigned as well. So the context for this is basically identify the specific functions that are not captured. You can capture them. And then this one, again, the downside is it could be complex. So considering functions and interfaces takes time and consideration. So I think these are more or less what are the benefits and what are the downsides of these processes. So in one, you can do it fast, get more alignment quickly, but then at the same time, the context may not be clear. Okay, so let's look at the essential component analysis in detail. So this is an example flowchart that you can apply to justify the parts in the design. So you can start with the component and ask question, does this part move relative to all others parts in the assembly? So you can go through this flowchart. Is this essential for the design of the, is this essential for the product function? Is it required for the movement? And just go through and kind of come up with a outcome that says non-essential or essential, right? So you're starting with the component, looking at movement, looking at material, looking at adjustment, and so forth. So how do you measure your design efficiency? So in addition to component analysis, you can see, well, how do I rate? If I start with a product that has 10 parts and I follow this approach and go down to 5 parts, how would I basically define the design efficiency? So typical design efficiency in R&D when you are working on a concept, so from concept to R&D is typically 25%. So you tend to have more parts than you need. So if you have a design that has 10 parts total, but essential could be 5, so that's like 50%. So, you know, from statistics, it's known that 25% design efficiencies are there in R&D phase. World class tries to get at 60 to 70. So what it means that you will end up having some non-essential components in your design, but the goal is to not eliminate all of them. Goal is to minimize, and then more importantly, justify them. So you know why they are there. They may provide some feature that may be optional, or they may be related to risk management. They may be related to simplifying the design. So there are various reasons why they exist. The goal is not to eliminate, like I said, it is to reduce. Okay. Detailed functional analysis, we spoke about that. So it kind of looks at functions and performance of each component in relation to the manufacturability. So what are the key steps to do the DFA? So obviously understand the component's functions, identify critical functional requirements. You can evaluate alternate designs, also do some risk management techniques like failure mode analysis, assess the manufacturing constraints. So if you look at a pen, for example, right, and you look at their parts and the relationship of various components in the design of this pen, you know, you could think about, do I need a spring? Do I need a ball? Do I need a clip? And how do they interact with each other, right? So relationship between these components, the technique to use is to use linking verbs. So plunger transmits force to ledger. Some of the examples are given here. Lower barrel retains the spring. So as you're defining the functional statement to capture the relationship between the parts, you can use this action verbs or linking verbs that connect them together. So when you do this, you can come up with some kind of, diagram as well. If it's easier, you can say ball controls the ink, right? The ink marks the paper. Clip is help to secure the pen to the pocket. Button cap, user presses button cap that presses plunger, activates ratchets, all these kind of things. So when you kind of define this relationship between the components and assemblies using these linking verbs, you can come up with, okay, do I need this or not, right? So also you can identify if there are missing functions. So sometimes you may have a design where you might not have considered some functions and you can add more functions to it, right? So here value engineering differs from DFMEA because there is another concept of value engineering, which is related to post-launch cost optimization. So the products in manufacturing and the manufacturers, typically big company, they look at the product and say, okay, how do I reduce the cost? So they will do a value engineering and kind of maybe more of a reverse engineering way than when you're designing from concept to prototype. So in this case, obviously, once you identify all the functions, and you pretty much know which function can be fulfilled without a component or assembly, right? And can you preserve those functions by reassigning some of the components to the same job? So in this case, the pen example, you can eliminate clip that is perhaps hard to assemble or breaks easily or comes off by having an integrated clip, which is more connected to the barrel in the plane design like this. So that's kind of how you follow this functional component analysis and essential components approach. So I went into a little bit detail just to give flavor of, when it comes to when it comes to focusing on product design, so we can eliminate some components, you can also combine some of the functions. The third one is operating environment, where you need to make sure the design works in all operating conditions. So how do you assess product to make sure that it will work in all normal operating condition as well as special operating conditions? So obviously design of experiment plays a big part in there, where you can test the design parameters by varying some conditions to optimize the performance. So looking at temperature range, dust particles, vibration shock, physical stress, all those kind of things. Even for maintenance, you can consider a few variations there. Some considerations here, obviously reliability and repeatability, part orientation can also help you in terms of making sure that the design functions in intended operating environments, sealing protection, mechanical stresses, all the testing and some simulation you can also do to make sure the design is suitable for the operating environment. So that was the third kind of area or category of key BFM principles we looked at. Product material, the goal here is to finding the best suitable product material. So how do you choose the best material for the product based on your design, based on your functions, environmental requirements, also economic considerations. So the material selection and analysis can also be a structured process where you define the requirements first and then follow a screening process. So you could look at 5 materials that you have shortlisted. You can collect the data on them, then do the screening, apply some constraints. So you may have some operating condition considerations. It has to operate in a certain temperature range. You can also identify significant parameters, compare them with your product design, also do some other screening aspect. Then you can rank them. And then obviously based on the rank, you can shortlist and then select the material. So you can be more structured and systemic in your approach. So you can use techniques like life cycle cost analysis, life cycle cost assessment as well. I have not used them much in this context, but yeah, certainly there are more techniques in terms of how you go about selecting the right material. Some of the considerations, obviously, are machinability, whether it's aluminum or steel, or plastic. Do we have some machinability considerations, affordability from a cost perspective, supply chain in terms of availability, transportation, weight can play a big role in there. And then sometimes if it's um, glued together, how strong the glue is going to be, which material can be glued easily compared to some other material. So these are some considerations you can think about when you're applying the screening process. Now, compliance and testing. So goal obviously is to meet the safety and quality standards. So what are the safety and quality standards applicable? What is the test criteria? So adhering to establish test criteria and guidelines so that we can ensure the safety and quality is how you meet the standards. So design verification validation, needless to say, we do a lot of design verification validation in medical device product development lifecycle. So defining the test requirements, criteria, creating a V&V plan, obviously doing some simulations, prototyping, inspection. If there is a design validation that's required from environmental compliance point of view, biocompatibility testing or other type of testing, you can consider those and make sure your design meets those. So considerations here, how do you detect the defects early? Is there going to be rework as a result of that? Can you scale it? Can I maintain regulatory compliance? Is there compliance data that's already available you can leverage? So some of these considerations go into this category of DFM principles. Okay. So in summary, what is DFM? It's a proactive approach in early design stages. It's basically used for designing the products for ease of manufacturing. It reduces cost and complexity. Why startups in early stage companies should bother about DFM? Obviously, because of strategic advantage, compliance and certification, making sure your products are compliant, resource efficiency, resource optimization, and increased chance of success. What are the key principles? We looked at the manufacturing process, selecting an optimal manufacturing process, product design, optimizing design through the functional analysis and the essential component analysis, material selection. How do you select the material through a screening process? Operating environment. How do you go about finding the components that are suitable for operating environments? And obviously from a compliance and testing point of view, following a structured process to define the validation requirements, verification needs, and then going about it. And then how to leverage the DFM. So the key to leverage DFM is obviously starting early, being more proactive, engaging with manufacturers, engage with them, analyze their processes, work with them, get their feedback, optimizing the design. Obviously, we looked at those two processes again, applying some engineering technique, and then planning and executing this and documenting the assessments. So that's how you can leverage the DFM. Some closing comments. Obviously, understanding the impact of DFM on a product design is a key. So the sooner you understand the impact, the better it is to design the product in a way where you can benefit from the DFM principles. Best time to optimize the product is while it's still in design phase, prior to incurring any manufacturing costs. If you want to avoid delays and longer cycles, it's better to just kind of start early again, and then optimizing the design phase. Talking to manufacturer will make the design transfer smoother, as I mentioned. Effectiveness of DSM consideration can reduce the resource burden, expedite transition to scalability. So if you consider DFM, you might need less resources in the long run, and also expedite the transition and scale from 100 to 1,000 units. And then obviously working with external partners like IZIL who know how to achieve DFM, it's essential. So you can partner with them, consider companies like IZIL or some consultants, and then just get an idea in terms of how you can go about it.